Hello, and so second video on this lecture that describes the transition from integral to differential calculus. And so now what we have to do, we know what are integrals, how to define and construct the area below a graph of a continuous function and also a monotone function and many other functions, but we are almost completely unable to compute the actual value of the integrals. Why? Because we just developed these techniques of performing the computation for lower sums, upper sums, and then compute the upper integral, the lower integral, and then to see whether they coincide or not. And this is very long. This is very costly from the point of view of computation. So we want to develop another method, which is more complicated from the point of view of the theoretical structure, but much, much more effective. So the title here of this chapter is Towards the Computation of Integrals. And this part will end with the statement and the proof, a very important proof that you have to learn, of the so-called fundamental theorem of integral calculus. The starting point is a notion of integral average or mean. So here I give you a definition. So we have a function f from, as usual, a closed and bounded interval ab up to r, an integrable function, and we define a quantity, so the following quantity that I denote by mu f of the interval ab, and it is the ratio between the integral and the length of the integral of integration b minus a. Okay? Is called integral average. Or min. And so this is the graph. Here you have the interval AB. Oh, there is a problem here. Here you have the function defined on A, B, the interval, and here you have the graph of your function f. Suppose that it is continuous. This is f. And so you want to compute this area. How can one represent the integral mean here in this graph? So you have just to note that the definition of the integral average can be modified by multiplying both members by b minus a. And so you have that the area below the curve is equal to the product of the integral mean times the length of the interval. Geometrically, this is the area of a rectangle whose basis is the interval a, b. so that the length is b minus a, and whose height is mu f. So mu f here as the level of the height of this rectangle such that the area below the rectangle exactly equal the area below the curve, which is the integral. Remember that the area computed in this framework, in this theory, is not always positive, can be negative. Okay, for negative values of f, that correspond negative values of the integral, negative contribution of the integral. Okay, and you can also notice at least a formal analogy with the usual mean. So if you consider the integral to be a sum, a sort of continuous sum, when you compute the average of n numbers, you sum all n numbers and you divide by n. Here you compute the area, so you sum all the infinitesimal area and divide by, so to say, the number, the measure of the infinitesimal area you sum. This is only sum, this is only formal at our level, okay? Don't take it too seriously, just to remember what is the formula here. And so why is this integral mean important? First, there is a theorem. Of course, we have plenty of theorems in this course. So the theorem of the integral mean, this is the name. Again, the only hypothesis is that you have a function f from AB to R, which is integrable and first you have that the mean, the integral mean of f is sandwiched between the infimum of f in AB and the supremum of f, again, in AB. This is quite obvious, at least from the picture here, but of course it has to be proven. Second, if, moreover, the function f is continuous, then there exists a C, a point C in AB, such that at the point C, the function f takes exactly the value of the mean, equals the mean. Okay, let us go with the proof, which is very simple. And this is a proof which is easily required of the oral exam. So we start with the proof of the first statement here, the fact that the mean is included between the infimum and the supremum of f. So infimum, so consider P to be the so-called trivial partition, which is the worst possible partition of the interval, which is made without adding any points between A and B. So this is just A, if you want, in our notation, this is equal to x naught, and B, this is equal to x1. Okay, so as a picture, here you have A, B. Here you have the function. Okay, and which are the lower sums and the upper sums? So the lower sum here will be as follows. Take the infimum. Remember that if the function is not continuous, we are not guaranteed that there exists a minimum, but of course, since the function is bounded, being integral it is bounded, there is a finite infimum. So this brown area here will be the lower sum. This is the infimum of f. On the other hand, corresponding to the supremum of f, we can represent the upper sum. Oop. I have it refuses to draw a straight line. Oh, here it is. Okay, this green area here is the upper sum. So this is S, Fp, because this is the supreme. Okay. So now it is very simple to find the result. Why? Because here we have that, of course, the lower sum cannot exceed the integral, and it cannot exceed, the upper sum. But who is the lower sum? It is the infimum of f in AB times B minus A. And this is equal, the upper sum is the supremum of f, AB, B minus A. Now divide by B minus A everything, here in this chain of inequality, and here you have that the infimum of f in AB is less or equal, so ignore the two sums and go directly to the member with the integral. This is equal to 1 divided by b minus a, integral between, this is a minus, a and b, f of x dx, less or equal the supremum of f in AB. And now observe that this is mu f in the interval AB. So you end up with a theorem. Okay. So point 1 is proved. Now we go to point 2. Now suppose that f is continuous and just use the intermediate value theorem. And you know that, first of all, f has a minimum in this closed and bounded interval, and of course a maximum too. This is the Weierstrass theorem. But moreover, the range is an interval. So every value between the minimum and the maximum is included. So this is the range of f. Now, by the previous point, by 1, we have that mu f in AB is included in this interval. But this is the image. So since mu f is in the image, it means that there exists a C in AB such that f of C is equal to mu f AB. And this is the end of the proof. So one has to well understand this theorem, the integral mean theorem. So I give you some examples, and again at the exam, especially in the second exercise of the written part of the exam, there are often exercises on the integral mean theorem. We like it very much. So as a first exercise, I show you this example. If you have f of x equal to -1, one instance in the interval -1, 0, open at 0, and then 2x plus 1 x 0, 2. So the first point here is compute the integral mean of f. In the interval -1, 2. Okay? And so first of all, let me draw the graph of the function f. So this is the value -1, it's -1, 0. And then in -2 we have 2x plus 1. Sorry, in 0, 2 we have 2x plus 1. So here it is, 2x plus 1. This is the function. And so we have to compute this area here. And now, so we still don't have a powerful and general technique for integrals, so we compute the integral by exploiting their interpretation as the area here below the function. Okay, and now the area is very simple to be computed, because here it is obvious that this area is 1, but here the function is negative, so the contribution here is -1. It is a square. On the other hand, this is a trapezoidal area, so we have just to take into account what happens is that here the value is 1, here it is 2, and here it is 5. So we have that this length, the so-called upper basis, is 3. The lower basis is 1. And the height is 2. So the area of this trapezoid here is 3, Sorry, it's 5, not 3, sorry. Is 5. Five plus 1 times the height, which is 2, and everything divided by 2. So it is 6. So the total area, of course, taking into account the sign, is equal to -1 plus 6, which is 5. Therefore, we conclude that the integral between -1 and 2 of f is equal to 5. Okay? And the integral mean of f in the interval -1 and 2 is equal to 5 divided by the length of this interval, which is 3. Okay? Okay. The second question is there any point, let me call it x bar, in -1, 2, such that the value of f on x bar is equal to the integral mean? So here from the picture we easily see what is the range of the function. The range is made by the point -1 and then all points between (1) and 5. So, in this case, what we have is the following. The range of f is equal to -1 union the interval between 1 and 5. And this, of course, includes 5/3. So therefore, such a point x bar exists. And I want to stress this fact, even though f is not continuous, because it has a jump. This is not in contradiction with the theorem, of course. It is not possible to be in contradiction with the theorem, as long as the theorem is correct. Because, not a problem, because what we proved, that f is continuous. If f is continuous, then there exists x bar such that f of x bar is equal to mu. Let me just call it mu without any, okay, mu f a b. Sometimes mathematicians are lazy of writing everything, but let me be clear, okay? But we did not prove the contrary. we did not prove that this property here is true only for continuous functions. There are discontinuous functions that can satisfy it. Very simple. But let me provide another example which is more or less the same. There is some change in the definition of f. There are some change here in the definition of f. So we have -1. This time we go to -3, 0. This is -3, 0. And then for the rest, the function is the same, so we can copy also the graph and then modify it. Again, because some mathematicians are lazy, but the lazier they are, the more genial they are. So be careful. Don't trust lazy men or women. Okay. Don't underestimate them. Okay. Here we start from -3. So the area we want to compute now is different. This. No. Okay. The area we want to compute now is here -3. Here it is again 6, like before. So the integral now is 3, and mu between -3 and 2, mu now is 3 over the width of the interval we are considering, which is 3 plus 2, so it is 5. And again, the range of f is equal to -1, union is like before, from 1 to 5, including the extremes, and this does not contain the average. So, in this case, there is no x bar, such that f of x bar is equal to the average mu f -3, 2. It happens because f, no problem, f is not continuous. So it is not obliged to fulfill this requirement of taking exactly the integral average as a value. And I would say that this is all for the integral mean theorem. So we are left only with the very important fundamental theorem of integral calculus, but I need another video for that.